Buongiorno a tutti. Inizio una brevissima presentazione della relatrice di oggi per i webinar di IBBR, la dottoressa Estefanía Núñez Carmona. Estefanía ha 2 dottorati, uno in Scienze, Tecnologie e Biotecnologie Agroalimentari e visto che si è decisamente appassionata alla parte anche di ingegneria e di fisica, ha preso un secondo dottorato in ingegneria dell'informazione e in fisica sperimentale. Io e Stefania ci siamo conosciute tantissimi anni fa ormai. Lei era in Italia per un Erasmus, io tornavo invece in Italia dopo il mio dottorato a New York, e abbiamo scoperto di avere una passione in comune per i sensori e che il nostro modo di lavorare era molto sinergico e spontaneo. Circa verso settembre-ottobre di quest'anno festeggeremo i nostri 10 anni di collaborazione insieme. E con estremo piacere che quindi lascio a questo punto la parola a lei. Oggi il webinar si chiama appunto Nanotechnology and Eco-impactless Approach in the Agri-food Field Monitoring. Please.
Okay, thank you so much for the presentation and for the opportunity that all the group of seminars from IBBR has given me to present my work of today. As Veronica says, is a long-term relationship between us and a really shared passion for sensor. So I start and this is just a bit outline of my talk of today, in which I will talk about something of nanotechnology and how it can be related to the agri-food field, but not only, and how we can use nanotechnology, but in this case in an organic way, to develop a new kind of technology. I want to show you the next 2 pictures. And those are two twin domes. One is the Biodome in the right part of the slide of Montreal, and the other one is the Steel Pavilion in Tel Aviv in Israel that has been created by the team of Professor Neri Osman. There are 2 radically and opposite cultures of design and architectural technology. One is made up of thousands of steel parts, and the other from silk, from a silk thread. One is synthetic, the other one is organic. One imposes itself to the environment, and the other one created. One is designed for nature, and the other one is created by her. But what really happens when we reduce it to the nanoscale? Well, let's see. In these 2 pictures, we find different kind of nanostructure. In the right part of the slide, we can see a 3-dimensional network of a metal oxide structured in shape of nanowires, while in the left part of the slide, we see a huge number of packed organic fibers. It's an organic material that we will discover later what it is. So, as humans, we have passed through different stages in the history. We have passed the Stone Age, the Bronze Age, and the Iron Age. But now I want to think that we are in the next step. That is the nanotechnology age. Well, I want you to see that in the bottom picture, there is just a single suspended platinum nanowire bridge suspended between 2 pools. And this picture for me encloses a huge quantity of beauty, because as you can see, it's just a single wire that is so thinner that it could be called that is quasi one-dimensional material. So every one of us, as many of us are biologists, have moved from the living scale that could be meters or millimeters until the micro world, when we find many different microorganisms. But what happens when we move to the nano world and actually to the quantum world? One could think that actually when it comes just to a single crystal of tin oxide, a metal oxide that are circled in the right part of the picture, one could think that actually or expect them to be rigid, difficult to shape, and brittle to break, but instead they are really flexible. And when we move to this scale of the nano world, we discover that actually the optical, mechanical, and electrical properties of the materials change completely. But how we move from the macro world to the nano world? Well, you already seen 1,000 times this picture. Is the Pietà of Michelangelo, and Michelangelo says that when he sees a block of marble, actually he doesn't see marble. He's seen a sculptor that was fighting to come out, and just Michelangelo, dotated with a hammer and a chisel, was able to take out from the marble this spectacular sculptures, creating powder. Well, to arrive to nanowire, we can use these two different approaches. One escaping and the other one using the powder. And we came to this. The top-down approach in the right part of the slide, that is the one that completely could be compared to the approach that used Michelangelo's, and the other one is the bottom-up, where we take the powder and we grow our nanostructure, and mainly is what we do. We create this metal oxide nanostructure to create what? To create MOS. That MOS is an abbreviation of a bigger number that they state to metal oxide sensor. Actually, this kind of sensor are gas sensor, and the nanotechnology that we use in this kind of sensor serve as a sensing element. These are made, as I said before, by metal oxides, and this metal oxide actually has a really good property, the property that became semiconductor when they are heated to huge temperatures that stay between 250, 300 degrees until to 400 degrees. Yeah. So actually, this kind of sandwich shape just in the right part of the slide is our sensor. It responds, giving an electrochemical response. So when the sensing part that are the nanostructural metal oxide are heated at high temperature, are able to interact with the surrounding environment, in this case with the surrounding gases, and create an electrochemical signal. In this case, we receive the signal as a change in the resistance of the sensor. Another thing that I want to you to pay attention to it is the sensing part is deposited in the alumina substrate that actually serve just to aside to deposit the sensing element. Afterward, we have the heating elements of I told you it was high temperature, and the electrodes all over to record the signaling. Well, this brings us to another concept, that is this one. Is the 1 trillion sensor economy. Our daily lives today are really managed and controlled by sensors. That means that by the last year, we reached 20.8 billion of sensors, and the National Science Foundation of the United States of America say that we will reach sooner the 3 trillion sensors, changing the term of Internet of Things to Internet of Sensor. Well, actually, I would like to think that it's not just Internet of Sensor, but another kind of Internet that I will show you later. When I started to work in this field, I read one sentence that impacted me so much, and it's this one. This sentence was said by Alexander Graham Bell in 1914, and it said, "Have you ever measured a smell? Until you are not able to tell me how a smell could be different or similar to another, you will not have a science of odor. And if you are ambitious to find a new science, just try to measure a smell." And that's what we try to do in these years. I'm quite sure that all of you have seen or kind of could guess what it is. This is a microbiological metabolisms map in diverse environments, in which every one of the dots are a metabolite, and every line that links the dots are an enzyme that converts one metabolite to another. Well, as you can see, there are thousands of those here, but some of them share a common characteristic, and this is to be volatile. So some of them are really volatile, and that brings us to another concept. That is the concept of volatiloma. Volatiloma refers to all of volatile metabolites and other organic or inorganic compounds that originate from a natural or artificial matrix that could originate or food organisms or even an ecosystem. Volatiloma and volatilomics is a science that has been defined not so long ago. It's quite young, and actually it's just a branch of what every one of us know now, that is metabolomics. Well, putting together volatilomics that actually are like fingerprints, no, volatile fingerprints, sensor and nanotechnology, we have put two aims that are these ones. The first one was to develop a setup to be applied in the framework of quality control in the agri-food sector and environmental monitoring, and the second one, more ambitious and more risky, that was to project and design and create a prototype of a new generation of organic moss from a green, innovative and zero environmental impact perspective. Well, let's move to the first aim. And the first aim has been carried out in collaboration with the nanosensor system startup. We have created together this device that is 3 device that stands for a small sensor system. And mainly the green device that you can see in the top part of the slide is just a lab version of our environment. Our sensors has not just the nanoscale for the sensing element, but are nearly 1 millimeter square in dimension, so they are really little. The core of the sensor is the sensor chamber that by now it can stand around 10 sensors. And that are all tailor-made, and we choose the sensor in basis of the morphology, the temperature, and the materials to have different answer. And depending of the application, we choose the most performing sensor array to the determinate application. Well, as I said before, our sensor gives a response in terms of changing of the resistance. The device is also equipped not just with a sensor, but is connected to a web app through an autosampler via CPU. And the web app allows us not just to store data, but also perform multivariate and univariate analysis. And yeah, we have also a pump that moves the volatile compounds from our sample until the core of the instrument, that is the sensor chamber. And as said before, our sensor could be 100% tailor-made regarding the temperature of operation, the shape and the material. And that means that we have obtained different response to the same to the same sample in order to cover the maximum volatile compounds possible, since not all the sensors respond in the same way to the same volatiles. So just to give you an example, we have here two response of different sensors to the same samples, okay, in which in the left part of the slide we can see an RGTO that was just a simple deposition of the sensing layer, while in the right part we have a nanowire sensor with a sensing element shaped in nanowire scale. So as you can see, both responses are different. So just to give you a hint of the main field in which we have already applied those, we have moved to agri-food sector, guaranteeing indigenous name, origin, and quality and safety of products, doing it in real time or at line, environmental monitoring for water and indoor and outdoor environments. And as I told you before, I would like to introduce another concept, that is the Internet of Food. That is the real-time verification devices for preparing and storing food in domestic or industrial environment. So our food connected directly to internet. And also we have applied this kind of technology to biomedical field regarding the diagnosis on early monitoring. For example, one of the applications, the last application, was to monitor the development of the dialysis of peritonic dialysis of patient, just to detect the early contamination of E. coli in this patient that is threatening life for them. Just to be more specific of one application, I'm quite sure that all you remember these cases of Campylobacter jejuni that was affecting many kindergartens in the Pescara region, in which 180 kids were affected with this sickness. And we asked ourselves if our sensor we will able to detect the presence of this bacteria. So we put together an in vitro an in vitro analysis in which we just take the lab conditions, so just inoculating the agent Campylobacter to the normal media, and we check it how the volatilome, the volatile fingerprint of the sample changes through time, using not just sensor but also classical techniques as GCMS and plate count, just to see which was the evolution of the number of cells and also the volatilome, to give a number and a quantity of the and quantify the volatile compounds created. And these are the results for the classical techniques, in which we see that for GCMS at the beginning we follow the development during 21 hours, and as you can see, the correlation between the two samples at the beginning was high because the number of cells was so little and still not detectable for the volatile part. They didn't start yet to produce any single compound, and at the end of the analysis the correlation was so low, arriving to 0.2. The compounds that we have detected that they have created neoformation compounds were normally alcohols and ketones of a low number of Cs, and normally are really volatile, as well as pyrrazines. And we have detected also that the number of CFU by milliliter has increased of 3 orders of magnitude. But which is more interesting is the sensor response that we have obtained, and we have obtained this graph. Okay, this is a PCA graph that you can see. Summing the value of the PC1 and the PC2, we can obtain that inside the graph is enclosed nearly the 99% of the explained variable. But like this is not so informative. I want you to check that all the green dots belongs to the contaminated samples, the inoculated sample, and are numbered regarding in chronological order. So if I compare this PCA to this kind of graph, I'm quite sure that all of you recognize this graph, and is the normal development growth curve from microorganisms. And we can follow, using this technique, every single step of the microbial development. As you can see, the main, one of the most impressive things of this graph is this part, and the last part, that actually in the stationary phase, the dots start to be overlapped, saying us that actually the volatilome present inside our sample was changing just a little. And the last part of the graph corresponds to the death or decline phase, in which the number of bacteria starting to decrease, so they started to produce less volatile compounds that are more related to the ones at the beginning, so they are above to the positive axis on the x-axis. Well, so just this image to show you how nanotechnology could impact in so many different aspects of the sustainable development goals to be reached by 2030. But I told you that we have also go further and try to develop new technologies going through zero-impactless perspective. So how we have done this? We have done this using circular economy. I will not annoy you with economical theories and so on and so forth, but the most simplest one is the one given by MacArthur, that actually is the mom of this kind of theory, in which you can see circular economy is an economy that is able to regenerate itself. You can see two streams of materials, one is technical and one is biological, but in the middle you are able to see that waste separate and waste separation and disassembly go together with some compounds coming from the biological pathway, going together and performing organic pure synthetic materials. So our sensor, as you can see, as you have seen before, work very well, but have some points in which we can improve something. In this case, the one that impact the most at the environmental level is the alumina substrate. That actually alumina is extracted from bauxite, that is a really stable mineral that create perfluorocarbons during their extraction. Perfluorocarbons has 9,200 times more harmful impact than carbon dioxide in terms of global warming. So, apart from this, also I have said before that this sensor works at between 250 and 450 degrees Celsius. So we put our attention in changing the substrate, and we went to use another kind of nanotechnology, using a biopolymer. In this case was bacterial cellulose extracted by from this kind of microorganism that this has a hell name called Comataeibacter sucrofermentans, and our biopolymer, as I said before, it was bacterial cellulose. This microorganism was started first time from the blueberries vinegar from China, and this kind of bacteria are aerobic, so they develop in the interface between air and media, container media. And the most important advantage in of bacterial cellulose when comparing with vegetal cellulose, bacterial cellulose is extremely pure. It has no lignins or hemicellulose, just cellulose street, and it gives us a huge advantage, that is actually the property that can stand around 350 degrees Celsius before decomposing, that as the thermogravimetric analysis says. And as you can see, it's a hierarchical structure, again nanostructured, so molecules of glucose are linked together by 1 to 4 beta linkage and structurate themselves in a hierarchical way that are taken together by the hydrogen bonds. Well, how these bacteria produce our cellulose? It produces our cellulose like this. Protofibers are extruded from the body of bacteria, and as long as they came out, they entangle together and form the our biopolymers. And this is the normal media that is used to grow this kind of bacteria, but as the literature says, it could be completely changed using food industry waste. It has been reported that has been used waste from beer industry, rice industry, and also citrus industry using orange peels to feed this kind of bacteria. So not only avoiding to use alumina, we reduce the impact, but also taking out the waste, using as a resource. So how do we create our substrate? We inoculate our bacteria in a rich medium. Afterwards, we harvest after 7 to 10 days, depending on how thick we want our mat of cellulose. We go after a bleaching time using sodium hydroxide, and afterward we wash it and we obtain what is called hydrogel. That is mainly a mat completely hydrated with water. Then we go to a drying process and we obtain our substrate. Making intervention in the different step of the production, changing the carbon source, as I said before, the time and the kind of bleaching, and the kinetic of the drying, we can it allows us to tailor the thermal stability, the structural properties, and the nanostructure of our substrate. Well, so after we obtain our substrate, we wanted to investigate the nano properties and the nano shape of our substrate, and we went to make our SEM image of our sensor and of our substrate, sorry, and this is what we obtain. We obtain a SEM image, and we can see all the cellulose fiber entangled between each other, and still some cellular bodies still entangled in the middle. This was the down part of the cellulose mat because it's the only one active. And we went further, also making SEM analysis and AFM, and we obtained this. The A picture represents just the upper part of the mat, in which we cannot see any bacteria, any microbiological body, because it was the inactive surface. In the B picture, we can see a cross section just to show you how packed the fibers are. And after all, we went to AFM, and in the C picture, we see 2x2 micrometers photograph, in which you can see a cellular body while fibers are coming out of the cellular body and are shrouded as long as the bacteria moves in the medium. And just the D picture is just the error signal of the AFM that actually highlight the fiber shape of our cellulose substrate that completely corresponds to the ones obtained before by SEM. After we move after we have controlled that actually our substrate are good to go, we deposit our sensing element, in which in this case it was deposited using magnetron sputtering. In this case, we use zinc oxide, and this has a really good reason instead of using tin oxide or any other material, is because using tin oxides allows us to activate our sensor not with the heat but with light, so allows us to perform our measurements in room temperature. So we have already reduced the impact of the alumina. We have taken out the waste of the food industry, and we have reduced also the operational cost of the sensor, avoiding completely batteries, because UV light could be created just using a LED lamp that has that needs really a low amount of to produce the light. So we move to deposit the sensor. We mounted it in the TO case, as you can see in the big picture, and we move to perform some tests. Okay, go ahead. Yeah. And we have performed the test in dark and UV light just to see if we were able to activate the sensor and using UV light in completely room temperature and using ethanol and acetone as gas tests using different pulses of different ppms, as you can see. And we have choose ethanol and acetone because are normally volatile compounds that came from the metabolisms of not all the microorganisms, but mainly all. And we have choose also hydrogen. Why we have choose hydrogen? Because as you can see, it will be the gas of the future, if you allow me to say that. Is called the hydrogen revolution that we need to reach sooner, as Ursula von der Leyen said, to power not only the transport but also our houses. And we have choose also NO2, that is one of the main contamination urban gases. So well, we went ahead and performed our test in our sensor chamber, and this is what we obtained. In the picture, you can say the sensor response in red to acetone and NO2 in growing pulses, and as you can see, as we increment the concentration of the gases, the response became always higher. Always focusing in picture A, what happened when we compare the same pulses when we perform the same experiment in dark, and you can see that the blue line is the response of the sensor to the same pulses in the dark, and it's completely plain, so no responses. Confirming again that the activation of the sensor using UV light is possible and it works. And just in the B part of the slide, so in the right part, we have we wanted to show you just the comparison between the different pulses of the gases and how different the sensor responds to the different gases. In this case, we obtain a good response to the NO2, even if it was just like 20 times less concentrated than acetone. So we have published this study, and we have already seen that using this kind of sensor has many advantages, as I told you before, not just reducing the impact, but also reducing the cost of the operational of the sensor. And as a conclusion, we can see that it was the first time that a photoactivated bacterial cellulose thin film MOX had been designed. The best response was sustained with NO2. And also it could be used to detect dangerous gas species in no heating environment. Just think about the hydrogen that becomes explosive at high temperature, and the leakage of this gas should be completely addressed before using it for public transport and in household environments. As a future work, we will try to new deposition techniques and to enhance the sensor, and why not, let's see further. Other application of the bacterial cellulose has been used to create OLED screens and the biological and medical environment, has been used to create scaffolds for burned people. So being just glucose molecules linkage between 1 to 4 beta linkage could be in hydrogel stages, just could be merged in a cell solution that could be used to transplant skin transplant for people that has been burned. And just approaching to the last slide of my presentation, I have always think on how we as scientists could contribute to this kind of environment. And yeah, I have like a dream. No, I would like to be able to produce this that are biodegradable edible sensors. This is just a prototype created by the ETH of Zurich. It's a normal sensor temperature based on organic polymers, and yeah, this is one of my objectives for the next future. And yeah, I haven't done this for sure not alone. I have a really good team that I want to thank, that are Professor Giorgio Sveglieri, Simone Pezzottini, and Marco Avatangelo, that are for nanosensor system, and of course my teammate Veronica Sperveglieri. So thank you so much all for your attention, and here are all my data. If you want to collaborate, we are willing to find collaboration between you. So thank you so much to everybody.